So the heating curve is when you raise the temperature of water or any liquid, but this one is just water. And cooling curve would be the opposite, where you have some given temperature and you lower it. So that's called a cooling curve. So you can heat or you can cool. Now for water, there's a couple of special points here on the y-axis, which is temperature. And the first one here is 0 degrees C. This is when you have both a solid and a liquid, so two phases. And then the second important temperature for water, the heating and cooling curve for water, will be 100 degrees C. Okay, at that temperature you have two phases, both the liquid and the gas. If you continue to heat, everything will become vapor. Just like here, if you continue to heat, everything will become liquid. So you continue to heat, or you can cool it. If you continue to heat, the energy that must be overcome here is delta H fusion. This delta H fusion is the energy for the phase change, going from a solid to a liquid. For water, this is at 0 degrees, and this delta H fusion is not it's not a number you need to memorize, but if in our notes it's 6.01 kilojoules per mole. Okay, from our notes. You do not need to know that number. And then if you heat, or you can cool it also, if you heat all the way to this second magic number of 100 degrees C, you'll get two phases. To overcome that phase and get it to completely vapor, you have to overcome, or you have to put in the energy of delta H vaporization. Okay? This is to help it get into a vapor. And that number here is a number you do not need to know. I'll give it to you on the exam, but this number here is 40.79 kilojoules per mole. All right. So that's heating of water, okay, or cooling of water. So we have two phase changes here. Okay. That delta H vaporization, most of it is going to disrupt the hydrogen bonds of water. All right, so let's go do this practice problem together. Okay. Something that's very similar on the test. This is calculate the heat released when 68 grams of steam at 124 degrees C is converted to water at minus 20 degrees C. So something like this will be on exam. Okay, so we'll have the exam review, but for now, just know we'll put extra attention to this. So one thing you should know from Chem 1, that heat is lowercase q. And if you release heat, what happens when you release heat? Where does that heat go? It goes to the surroundings, also the universe. And the system, if the surroundings get the heat, the system has a negative sign. Okay, this happens when you cool. Okay, this is a convention that was given by the thermodynamics people several decades ago. Okay. On the flip side, if you heat something, if you're adding heat or adding energy to the system that's heating, your Q will be positive. Okay, this lowercase q is heat. So in this specific problem, calculate the heat released. So what will the sign be? Positive or negative? Okay, it's going to be negative. We're going from 124 degrees C to minus 20 degrees C. Okay, so are we heating or cooling? Okay, are we heating or cooling? Okay, cooling. So 124 to minus 20, you're cooling. So where will that heat go? It's going to go to the surroundings. Okay, it will go to the surroundings, and that's heat released. Okay, heat released to the surroundings. The heat will be negative. All right, there is an equation here that I'll give you on the test. It's Q equals ms delta T. Okay, this S is a specific heat. You do not need to know the definition, but I'll give you the definition. We just need to know what it means. So let me give you the definition just for clarity's sake. Specific heat is the amount of heat required to raise 1 gram. So this is specific for 1 gram. Required to raise the temperature. Specific amount of heat required to raise the temperature by 1 degree C on 1 gram of a substance. So the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree C. Okay? Amount of heat required to raise 1 gram of a substance, its temperature, by 1 degree C. So what we need to know, what's important for us, is that this is a constant. Okay? So it's a constant that will be given on the exam. We do not memorize any constants in this class. Okay? So water has 3 phases. Okay? It has a vapor phase, it has a liquid phase, this is its specific heat, and it has a solid phase for water. Okay, you may know this as ice. Right, and just be cognizant of the units, joules over grams degrees C. Okay, so amount of heat in joules required to raise 1 gram of a substance by 1 degree C. All right, so how will we do this problem? Okay, so we will not plug straight into this equation. Okay, we will not. Okay, what we will do is we will break this apart. Okay, we will break it apart. Okay, so we'll first, in this aqua color, we'll break it apart into the first heat. Okay, the first heat is 124 degrees to what, if you were to guess? 100 degrees. Okay, so we're going to call this Q1. Right, here we can use Q equals ms delta T. So the mass is 68 grams of water. The specific heat, we're going to use the specific heat of steam because from 124 to 100 degrees you mostly have vapor or steam. So we're going to utilize this constant, which is 2.02 joules over grams degrees C. And then final minus initial. This delta T is final minus initial. Okay, what is our final temperature? Okay, and what is our initial temperature? 124. Okay. So what is this on our calculator? Okay, grams cancel, the degree C cancels. We are left with joules. All right, let's do this on our calculator here. We have 68 times 2.02 times 100 minus 124 times, put the parentheses in, 100 minus 124. And I'm getting minus 3297 joules. Okay, you got that? Good. Okay, this is Q1. All right. So what is our next heat? Okay. Our next heat is we're cooling this. We got to 100 degrees. We're going to cool it all the way to the final temperature, which is minus 20. So at 100 degrees, we got from 124 to 100. At 100 degrees, what do we have? We have a phase change, okay? So this will be Q2. okay, Q2. So we'll do that in green ink. So phase change at 100 degrees. Okay, we're going to call this Q2. All right, so this is what we'll do. We have 68 grams of water. Okay, 1 mole of water contains how many grams? Okay, remember this from Chem 1. Hydrogen is about 1.01. Oxygen is about 16. So there's about 18.04 grams of water. You just add the numbers from the periodic table. And then what's the energy here? 40.79 kilojoules per mole. Okay. Let's convert that to okay, fine. Yeah, all right, let's just do this here. All right, 68 times 40.79. Divided by 18.04. I'm getting about 153.75 kilojoules. Okay, kilojoules. And let's 153.8, we'll say. Because this is in joules, I'll go ahead and convert this to joules as well. Okay, or you can keep it at kilojoules. And it's going to be 1 kilojoule is 1,000 joules. Okay? And what will that make it? About 153,754 or so. All right, so question for you guys. What is the sign here? This is something that will definitely can trick you. What's the sign? Remember, what are we doing? Are we taking in heat or are we giving heat out? We're cooling, we're giving heat out, so what should the sign be? Okay, negative. Okay, sign should be negative. Even though it's not here, it's negative. Why? Because you are cooling and the heat is going to the surroundings. Okay, so don't forget this on the exam. Okay, since we are cooling, we are sign is negative. All right, so now we have Q2. All right. So this is going to be our Q2. All right, so now we are at 100 degrees, and then we overcame that, you know, with our minus 153,000 joules. So now what is our next Q? It's going to be from 100 to what temperature? 100 to 45, it's minus 20. 100 to what? 0. Okay, 100 to 0. Okay, so we'll do that in red ink. Okay, so now we'll call this Q3, and this is from 100 degrees to 0 degrees. Okay, we're going to call this Q3. All right, so now we'll use Q equals ms delta T. Okay, the mass is 68 grams. Okay, we're going to use this one. Okay, we're going to use this one, which is the specific heat for water as a liquid, because between 0 and 100, your water is a liquid, and that's going to be 4.184 joules over grams degree C. And then final minus initial. Okay, what's our final temperature? 0. What is our initial temperature? 100 degrees C. Okay. So this is Q3. All right, so what is this on our calculator? Let's do a quick math on that. 68 times 4.184 times 0 minus 100 is minus 100. And I'm getting minus 28,451 joules. Okay, joules. Okay, the grams, degree C cancel. Minus 28,451 joules. Okay, this is Q3. All right, so what will be Q4 now? Okay, we got from 100 to 0. What happens next? Very good. Phase change. It's not 0 to minus 20. It's phase change. Okay? So the phase change is going to occur at 0 degrees. So we'll do that in, we'll do this in black ink, the phase change. So this is Q4. Heat 4. So we are at 68, right? 68 grams of water. Okay, times 1 mole of water is 18.04 grams of water. And what is this that we will multiply by? Okay, this is the phase change, delta H fusion, which is 6.01 kilojoules per mole. I'll give you that on the test. So it's 6.01 kilojoules per mole of water. And if we want to convert it to joules, it's 1 kilojoule is 1,000 joules. Okay. So always cancel out your units to make sure everything is okay. And what is this on our calculator? 68 times 6.01 times 1,000. Divided by 18.04. 22,654 joules. 22,654 joules. 22,654. Okay, this is Q4. All right, and then finally, what will be Q5? What will Q5 be? Okay, we are at 0 now, so what will Q5 be? 0 to what number? Minus 20. Okay, this will be our final one, and we will use, what ink shall we use for that? Okay, we'll use this orange ink. Okay. Q5 is 0 degrees to the final one in the problem, which is minus 20. Okay. So here we're going to use Q equals ms delta T. Okay, the mass is 68.0 grams. the specific heat from 0 to minus 20, we will use this specific heat of 2.06 joules over grams degree C, because why? Because most of the water is going to be in the solid state, spanning from 0 to minus 20. So it's going to be 2.06 joules over grams degree C. Okay, delta T is final minus initial. Final is what? Minus 20. What is initial? 0 degrees. So grams, degree C cancels. And what will this be on our calculator? 68 times 2.06 times minus 20. Okay, minus 2802. Minus 2802 joules. Okay, this is Q5. And now we have to sum up 5 heats. Okay, so to get the total heat in going from 124 degrees water to get it to minus 20 degrees water, how much heat is that water going to release to the outside environment? We're going to sum up Q1. Okay, we're going to sum up Q1, which is minus 3297 joules. Okay, that was an aqua, plus the phase change, which is Q2. Okay, this is confusing. So plus a minus 153,754 joules. 754 joules. Okay, it's plus or minus, so be careful. Okay, that's tricky. Okay, that's the phase change. And then plus Q3, which is going from 100 to 0 degrees. And this is plus a minus 28451 joules. Okay, plus a Q4. Which is, okay, what's the sign of this? Okay, it's minus because we're cooling. Because cooling, so it's going to go to the to the surroundings. Plus a minus 22654 joules, plus a Q5. Plus a minus 2802 joules. Adding all of this up will give us the heat released when you take 68 grams of water at 124 degrees and then cool it to minus 20 degrees. Okay, this is how much heat is going off to the surroundings. So let's add this up. Minus 3297. Okay, just be careful of all the math, because I'll make the calculator errors just as much as anyone else. Plus minus 153,754. Okay, plus minus 2851. Plus minus 654. Wow. Plus a minus 2802. Okay, so if I did it right, I think I did, I don't know. I definitely need someone to double check me. I'm getting minus 210,958. Okay. I'm going to convert it to kilojoules because I don't want to write all those numbers. So I'll divide it by 1,000 and I'll do minus 211 kilojoules. Okay, so you can do it on the exam, joules or kilojoules. I'll just write minus 211 kilojoules, and this is our answer. So can we do something like this on the exam? Okay, so we're summing up, in this case, 5 heats. Okay, sometimes you may just have to sum up 3 heats. Okay, sometimes you don't have to sum up any. Okay, it just depends on the nature of the problem. All right, any questions or comments? Okay, we'll go over this again for our test review whenever, or the day before the exam, or closer to exam time, closer in proximity to that. For now, the one you did at home, the one here should be good practice. All right, so lastly, is the phase diagram. So just really quickly, the phase diagram, as you remember from the video, we have pressure on the y-axis, we have temperature on the x-axis, and specific pressure and temperature combinations. So some pressure and temperatures, the x and y coordinates, you'll be a solid, some you'll be a liquid, some will be a vapor totally. In some cases you straddle. Okay, some cases, at some pressure and temperature combos, you straddle between a solid and a liquid. Okay, some pressure and temperature combos, X is temperature, Y is pressure, you straddle between liquid and vapor. Okay, and then in some you straddle between 2 phases, solid and vapor. Okay. And in some cases, called the triple point, you are all 3 phases, right? This is called the triple point. Okay, the one over here is for water. The one over here is for carbon dioxide. Okay, I know that because I remember it from your book. Water is interesting because water has this solid liquid diagram in the phase diagram bends backwards. Okay, so that makes water very unique. Okay. Most other substances, it will either be this way or slightly tilted clockwise, but this is bent backwards. This is the reason why I think ice is more dense. That's why you have ice and then you have water underneath, because ice is less dense than water because of this type of backward bending curve at the solid liquid phase. Okay? So just know the backward bending highlighted in pink here is very unique for water. Right, and I think the last thing I want to tell you is this vapor pressure temperature curve. All right, this curve, this profile is exactly the same as this. Okay, these are exactly the same. And if your vapor pressure is 1 atmosphere, okay, that's called the normal boiling point temperature. Normal means 1 atmosphere. All right, so those are the 2 things that I want you to know about the phase diagram. One is this backward bend of the water, and the other is that one graph that we went over earlier in class is exactly the same as this part of the phase diagram, liquid and vapor. So that's a wrap of this chapter. Make sure you do your homework, check your answers with the answer key. You can upload that, and I'll put in the 10 points. Okay, homework is just an honor system. All right. Is everyone okay if we move on to chapter 12? So this is a wrap of this chapter. All right, chapter 12 has to do with solution chemistry. All right, so I have here underneath me here in the drawer, I have 2 beakers. All right, one beaker is just a beaker of water. Okay, nothing big, nothing fancy. Okay, and then another beaker, I have another beaker with water. Okay, but I also have here a can of glucose. All right, so I pour water in here on my left-hand beaker, and we're going to call me pouring water here, we're going to call that water a solvent. How many of you have heard that term before, solvent? Okay, so what do you think that term means, solvent?
It's the thing that is being dissolved. Or no, or is it the other way around? Is it the thing that's being dissolved?
So we're going to call solvent here the dissolving medium. Okay, dissolving medium. Okay, dissolving medium. Is water a solvent? Okay, it can be. Is water the only solvent that exists on Earth? Okay, no. There could be many, many types of solvents. If you take organic chemistry, they use different solvents. Okay, but right now, the solvent is the thing that is being used to dissolve the substance. Okay, I have here some glucose, okay, just a glucose white powder that I bought from the store. Okay, just take some. Okay. Maybe I'll take a teaspoon. Yeah. Okay. So, did it go in? Did it dissolve? Okay. It dissolved, all right? So, how many of you have heard the term solute? Raise your hands if you heard the term solute. Okay, what is a solute in your estimation? Go ahead.
It's the medium that's being dissolved.
Solute is what's the solute? Okay, solute is the particulate that you want to get dissolved. Okay. Particulate or substance that you want dissolved. All right, so the solvent is the thing that is going to do the dissolving. The solute is the thing that you want dissolved. Okay? So do you think this has dissolved? Is it soluble or insoluble? Okay. So it is soluble. So what's the difference between this and this? Okay, you couldn't tell them apart. Okay, now in a lab we never taste things, but we can't tell them apart other than this is water and this may be sweet if we taste it. But they look pretty much the same. Okay, they look pretty much the same because glucose is soluble in water. Okay, now if I dump this whole thing, it's not going to be soluble. So, there's a solubility limit. Okay? So we have here solvent. We have a solvent plus solute. Because this dissolved, and there's virtually nothing different between this and this. I mean, it's slightly different, but you couldn't tell one from the other. Okay, we're going to call this a solution. Okay, solution. So solution is equal to solute plus solvent. As long as it's dissolved, you have a solution. Solution is equal to solute plus solvent. Okay, so that's the first important thing. solution is equal to solute plus solvent. Now, because water is the solvent, this has a special name. If water happens to be our solvent and it dissolves, which in this case it did, if water happens to be the solvent, we call this aqueous. And because the solute dissolved in the water, we call it an aqueous solution. Aqua, aqueous. Aqua, water, aqueous. Okay, so an aqueous solution is when the solvent is water. All right. So like I said before, there's many different solvents. It's just that in biology or in biochemistry, in Gen Chem also, we like to use water as the solvent system. But in organic chemistry, they won't use water as a solvent system. They'll use some organic, like, I don't know, ether or something like that, okay, oil or something. Okay, but if our solvent is water, if our solvent system is water, and it goes in, okay, it has to dissolve, has to be soluble, not insoluble, it has to be soluble, then you have an aqueous solution. Okay? So what we've done here is we've made a solution, right? Okay, we made a solution. Okay, one on the left is the solvent, water alone. The other on the right, okay, my right, is the solution. So what's the difference between these two? Are they the same? Well, obviously this one has glucose in it, and like I said, we don't taste anything in the lab. So how do we distinguish these two? Okay. Remember, we label everything. I was in the prep room just a couple of days ago, and there's just beakers just lying there, it's unlabeled. Like, what is that? So you can get in trouble, you can get fined if the inspectors come. So always label everything. Okay, but how do we distinguish between these two? Okay, if we don't label it. Okay. So let me ask you this: what's the boiling point of this water by itself? Solvent by itself, water. What is its boiling point? 100 degrees. Okay, 100 degrees. Okay, what will the boiling point of this be? Okay, would it be higher or lower or the same? Will it be the same, first and foremost? Okay, that's right. It's not going to be the same. Okay, but will it be higher or lower? Okay, we added glucose. We added a solute into the solvent. There is more IMF. There's more intermolecular forces. So what do you think the boiling point will be? Will it take more to get it to boil, or less to take it to boil? More. Okay, so the first thing that distinguishes this from that, the solution, is that the boiling point will be higher. So we call this boiling point elevation. Okay, the minute you add a solute to a solvent and it dissolves, the boiling point will be higher. We call that boiling point elevation. The second thing that happens when you add a solute and into a solvent system and it dissolves is your boiling point will go up, your freezing point will go down. Okay, so this is called freezing point depression. It goes down. Boiling point goes up, freezing point goes down. What do you think is going to happen to the vapor pressure? Go up or down? Okay, we added some solute to the solvent to make the solution. We have a solute now, we have a solvent in there, we have more IMF, more intermolecular forces. So will that make it easier or harder to become a vapor? Harder, because now you have solute, solute, solvent, solvent, solute, solvent, IMF to overcome to become a vapor. So if it's harder to become a vapor, Will that mean more vapor pressure or less vapor pressure? Less, okay, because you're just not forming as much vapor.
So that on the table, like right there, that we see like under like the solvent definition, are we going to need to memorize that?
I think if you know the basics, it's fine.
Okay.
Yeah, I try to minimize memorization as much as possible.
I don't think in science, I don't think that's like the most reliable on the thing.
Okay. So the vapor pressure goes down. Okay. And then finally, are there any biology majors here? Okay, in biology, there's something called osmotic pressure. So you develop an osmotic pressure in the presence of a membrane, in the presence of a semi-permeable membrane. So this osmotic pressure is called pi. It's called pi. I don't know why, but it's called pi. All right, so all these four properties, the minute that you add a solute to a solvent, and provided that it goes into solution, okay, provided that it dissolves, you'll immediately get higher boiling point, lower freezing point, lower vapor pressure, and if you put in a membrane, you'll develop osmosis or an osmotic pressure. So all of these four properties are called colligative properties. Okay, colligative properties of a solution.
So these all occur when exactly again?
When you make a solution, a solute into a solvent.
So basically, so anytime we just do like a solution, any kind of solution?
As long as it dissolves. Colligative properties. Okay, colligative properties, by colligative we mean this, like you can add a lot as long as it dissolves. You can add a little, you could add a speck. That solute could be the most complicated structure in the world. It could be the most simplest structure in the world. It could be a poisonous compound. It could be, I don't know, a life-giving compound. It doesn't matter. It could have a large molecular weight. It could have a small molecular weight. Okay, as long as it dissolves, and as long as that solute dissolves and forms a solution, these four things are going to happen. So by colligative, it doesn't matter how complex the solute is. Okay, this is universal. This is universal. Okay, as long as it dissolves that solute, whether it's ionic or covalent, whatever it may be, these four things happen. Okay, when you make a solution. Okay, I think we have a lab in a couple of weeks where you'll do a freezing point depression. All right. All right. So in this chapter, we'll focus on problems doing these four. Before we get into that, there's a thing I'd like for you to know, and that's called like dissolves like, and that's on page 2 of our notes. So let's go to page 2 of our notes. All right, just really quickly here, to make a solution, okay, to make something like this that's completely dissolved, you have to overcome some IMF, intermolecular forces. You got to overcome the solvent-solvent intermolecular forces and the energy required for that, the solute-solute intermolecular forces, and then those must be overcome, and then you'll get your solute-solvent. IMF has to overcome delta H1 and delta H2, okay? So this is not something I'm really, emphasizing, but just realize, solute, solvent, IMF has to really overpower solute, solvent, solvent. Okay, in some cases, to make that happen, you have to add heat. To make it happen, to make a solution. Sometimes it just happens so well that it releases heat. Okay, we call that an exothermic solution. So to make a solution, it probably requires heat. Example of this would be like urea in water, I think, or ammonium chloride in water. There are some solutes that won't go in until you really add some heat. Okay, the D stands for deionized. Releases heat, I don't know, maybe like sodium in water or sodium chloride in water. Yeah. And this is not something I really want you to know, well, I expect you to know, but just realize that to make a solution sometimes requires heat. You need to put in heat to make it happen. Sometimes it just goes in and releases heat. Okay, and this is all involving the IMFs, overcoming solvent, solvent, and solute, solute.
We're looking at this, when it says low and then high underneath, that's basically saying what it needs to do. So it means that no matter what delta H3 has to overcome the other two additives.
Correct. That's all I'm saying.
Okay.
Yeah. That's exactly right. Yeah, delta H3 has to overcome delta H1, delta H2. So the IMFs of the solute solvent must be greater than the solute solvent solvent. The energy for them to come together. Their IMFs must be greater than the other two. All right, here's something I'd like for you guys to know. I'd like for you to know that one as well, but this is something you'll see a lot in chemistry, and that is like dissolves like. It's something I'd like for you to know, and it's very simple. Okay, if we were to determine what can go into what dissolves into what, we will use like dissolves like. So ionic and polar go together, and nonpolar go with nonpolar. So that's all that is. Okay, a polar molecule will dissolve in another polar molecule. A nonpolar molecule will dissolve in a nonpolar molecule. So this is actually liquids with liquids. Okay. What we had here was a solid going into a liquid. So here, like dissolves like, is two liquids. Will they come together, or will they be like oil and water? Come apart. Okay, so here this like dissolves like focuses on liquids. Okay. And if they come together, we call that miscible. Miscible. If the two liquids mix. If they don't mix, and if they're like oil and water, they become immiscible. Okay, immiscible. Immiscible. Okay. How do we know if two liquids can be miscible or immiscible? Like dissolves like. All right, let's do some problems like this here. Okay, two liquids. Okay. All right, so just as a brief review, let's quickly review this before we go to page 3. Okay, solution is solute plus solvent. Okay, the minute you make a solution and add a solute, whether it's a tiny amount or a little amount, as long as it dissolves, you'll have these 4 things called colligative properties. Okay, the IMFs of the solute and solvent must overcome the individual IMF solvent and individual solute IMFs. And then we're talking about two liquids here. Okay, how do we know if two liquids that we've never seen before, will they mix or will they not mix? Okay, like dissolves like. Okay, and ionic and polar will go with ionic and polar. Nonpolar will go with nonpolar. All right. Okay, without looking at this, okay, let's see here. Oh, actually, without looking at both of these, okay? Okay, what do you think? Will C6H6 and H2O, will they mix or not mix? C6H6 is benzene. Okay, so will they mix or not mix? Okay, so they will not mix. Okay, why will they not mix? We call that immiscible. Okay, what is the major IMF for benzene? Okay, benzene looks like this. This is a carbon, but I'm not going to write it as a carbon. I'm going to write it as a little point. Okay, C6H6 looks like this. Double bond, double bond, double bond, H's. Okay, pretend this point is a carbon. All right, and water, we all know, is bent. Okay, so will benzene and water mix? Yes or no? Okay, they're immiscible, but why? Okay, why? Okay, because benzene is nonpolar and water is polar. What's the major IMF in benzene? Okay, dispersion. And what is water? You can say polar. That's kind of the right answer, but be more specific. More specific, polar and hydrogen bond. Okay. And like dissolves like tells us they will not mix. These are like oil and water. Okay. All right. How about the same benzene and CCl4? Okay. CCl4 is carbon tetrachloride. If I draw you the structure of carbon tetrachloride, what do you think? Polar or non-polar? The Cl's cancel each other out. Okay, if there's symmetry in the molecule, it's nonpolar. So we have nonpolar benzene, nonpolar CCl4. Will they mix or not mix? They will definitely mix. Okay. What about water and ethanol? Okay, both can hydrogen bond. Yes, they'll mix. Like dissolves likes. What about water and the CCl4? Yes or no? Okay, water, as we know, is polar. CCl4 is nonpolar. Okay, there's no net dipole moment. Okay, what about C6H6 and ethanol? Yes or no? Will they miscible or not miscible? Okay, C6H6 is nonpolar, ethanol is polar. Okay. Okay, how about sodium chloride and ethanol? Would they come together? Miscible or not miscible? Excuse me. NaCl. What is that? Ionic. Ethanol is polar. So this would actually mix. Okay, ionic plus polar. Okay, so the partial negatives of the OH, electronegative oxygens, will interact with the full positive of the sodium ion. Okay. All right. So here's something new here. This is kind of a departure. So let's kind of clear our brains for a little bit and talk about the last 10 minutes of class, or maybe 15 minutes or so of class. Okay, something that's different. How many of you have ever gotten blood work done and got your blood results back? Okay, everyone here. So they measure certain things, and they measure certain things with concentration. Okay, concentration. So they'll measure your sodium or your potassium or whatever it may be. Okay, but they measure a concentration. The concentrations that we use in chemistry a lot is molarity, which is moles of solute over liters of solution. Sometimes you'll see mole fraction, moles of A divided by the sum of all the moles. Okay, we'll see mass percent, mass of solute divided by the mass of the whole thing. Okay, to get it as a percent, you multiply it by 100. So all of these are units that tell us how concentrated something is. Okay, just the same thing when you get your blood report back. Okay, your glucose is measured in, I don't know, milligrams per milliliters or something. Okay, it's a concentration, or I don't know, milligrams per kilogram body weight. Okay, so there is some way to measure how concentrated something is. Okay, in chemistry, the most common one is molarity. which we talked about in Chem 1, mole fraction, and then this new one, which is a little bit difficult, is called molality. Okay, and this is moles of solute over kilogram of solvent, and this is lowercase m. Okay, lowercase m. Okay, these mass percent is easy because it's just the mass of the part divided by the whole. Okay, the mole fraction is easy. It's the mole of whatever you want divided by the mole of the whole thing. Okay, you multiply both by 100 to get a percentage. This molal and this molar can be a little difficult. All right, so on the exam, what will you say if they ask you the units for molality? What will you say? Solute over what? Kilogram of solvent. Okay, units, okay? Lowercase m. Now, on the exam, if they ask you the units of molarity or molar, what will you say? Over what? Liter of solution. Okay. So we have molality and molarity. These are the two concentrations that we see a lot in chemistry. Okay, we see a lot. This is how we measure concentration. Similar or analogous to when you get your blood reports back and you get a concentration of your potassium, sodium, glucose, calcium, whatever it may be. Okay, but in chemistry, these are the tells us how concentrated something is versus how dilute something is. Okay. All right, so let's do a problem here where we convert between molality and molarity. Okay, we're going to convert between one and the other. Okay. All right, we'll do these problems. Okay, they're a little tricky, but with practice, it should be okay. All right, so we have here 0.396 molal. Okay, I need everyone's attention here because once we get this problem, the other problems will be easier. All right, I just need you to be with me as we go over this together because this is new. Okay, 0.396 molal glucose to molarity. Okay, so we have lowercase m to big M. Okay, and they tell you the density of glucose is 1.16 grams over milliliters. All right, so here's how we'll do this problem. Okay, it's a little tricky. This 0.396 molal, what does it mean? It means 0.396 of glucose, moles of glucose. C6H12O6. I'll give you that formula for glucose. Okay, you don't have to memorize it. I'll give you that formula. Over what? What is molality? Moles of solute over what? Over kilogram of solvent. Okay. All right, so if you are not given a solvent, at least in this class, we can assume it will be water. Okay, so assume the solvent system is water. Okay, distilled water. Right, so this 0.396 molal is 0.396 moles of glucose. I'll give you the formula, so you don't have to memorize it. Divided by the kilogram of solvent. Without any other information, if they're purposely vague like that, you can assume the solvent is water, but I will make sure that, and when I write the exam, that the solvent is water. Okay, or aqueous. Aqueous. All right, so this is what 0.396 molal means. 0.396 moles of glucose in kilograms per kilogram of solvent. We want to convert it to molarity. What is molarity? It's moles of solute over liters of solution. All right, so here's how I'll do it. Okay, you may have a different way, but here's something that I'll show you how I'll do it. So one thing, this kilograms of solvent, okay, 1 kilogram is equal to 1,000 grams, okay, and the solvent is water. So this is the same thing as 1,000 grams of water, which is our solvent. Okay, 1 kilogram is 1,000 grams, okay, and this is our solvent. What is our solute? What's our solute? Okay, so let's convert the moles of solute glucose to grams of solute glucose, okay? So we're going to take this point. So we have here 0.396 moles of glucose, which is C6H12O6. Okay, 1 mole of glucose contains how many grams? Right, quick. 1 mole of glucose is how many grams? I don't know this off the top of my head. This is what I know. Okay, carbon is about 12.01, right? So 12.01 times 6 plus what's hydrogen? Yeah, 1.01 times 12 because we got 12 of them in the formula. Plus what is oxygen? 16. Yeah, very good. 16.01 times 6 because there's 6 of them in the formula. See, without our periodic table, we were able to guess with good, reasonable accuracy. The molecular weight of glucose is 180.24 grams, okay? And this is going to be this 180.24 times 0.396 moles. Uh, 71.38. I'm going to add some extra digits here. Grams of our solute, which is glucose. All right. So we have grams of solvent, grams of solute, and we know one thing that we do know is that the grams of solution equals grams of solvent plus grams of solute. Okay, because solution is equal to solute plus solvent. All right, so our grams of solution, we're going to take the 1,000 grams of water solvent plus our 71.38 grams of solute, and this gives us what, 1071.38. grams of solution. Excuse me. All right. So we have our grams of solution, and one thing that we also have in this problem is the density. Okay, the density of the solution. All right, so we have our grams of the solution, and we have the density of the solution. So let's use the density of the solution with the grams of solution to get the volume of the solution. Okay. All right, so we know that we have 1,071.38 grams of solution. Okay, our density is 1.16 grams per mil. I'm going to put the 1.16 grams at the bottom per mil. This is the density. Let's go ahead and convert this to liters. What is it? It's 1 liter is 1,000 milliliters. grams, mils cancel. So 1,071.38 shut up. Okay, 1,071.38 divided by 1.16 times 1,000. Are you guys getting 0.924 liters? Okay, 0.924 liters. Okay. All right, so what is molarity now? Okay, molarity is moles of solute over liters of solution. Okay, our moles of solute is still going to be the 0.396 moles of glucose.
One thing, why is it 71.38 grams or 1,071? I love the way you wrote it.
1,071.38.
Then why is it 1,070?
Because of this. Grams of solution is grams of solute plus grams of solvent.
Okay.
Okay, so moles of solute is going to still be 0.396 moles. So you add them up. You add the grams of solute plus grams of solvent. When I did that, I got about 1,071.3, unless I did the math wrong. That's why I need somebody to double check me. Moles of solute, which is that, liters of solution, which is this, 0.924. Okay, what do we get when we do that? .43 big M. Okay. And this is the answer, 0.43 big M. Okay. So 0.396 molar of glucose. Let's just add one more digit. Let's do 0.429. 0.429 molar is about the same thing as 0.396 molal. Okay, 0.396 molal of molal. Okay, of glucose. The reason why I did 3 decimal places, because the molal, what they reported in the problem is 3 decimal places. Okay, but on an exam, I won't be that picky. So 0.396 molal glucose solution is the same as 0.429 molar glucose solution. Okay. All right, what time do we have here? What is it? 10:43. Okay, so class ends at 10:45. We'll do these 3 problems. I think what I'll do is I will give you the answer to this, and you can work at it from home. And then we'll do these 2 together, and then I'm going to skip pages 5 and 6 of our notes. Okay, so you can skip 5 and 6. You can put a line on them. Pages 5 and 6.
Okay, thank you.
And I'll give you the answer to this. You can check the answer and work the problem and see if your answer matches what I got. All right, I'll see you in lab today. I'll try to be there by 1:30 to 1:45. Okay? I noticed that we got to turn on the computer, so computers take a long time to boot up.